I'm going to give a story on a trip to our headquarters that we received from the Human Language Authority of an intelligence agency. The lead and both of his immediate assistants, all mission linguists for the intelligence community, came to our headquarters. And early on in that day, I emphasized that we weren't going to put out a lot of proprietary information markings or anything like that. That much of our company really, what specializes us, the techniques, the algorithms, the deep learning, you can go to the academic literature and learn how to do it. But it's the actual doing of it. And all of those multiple dimensions that I talked about with respect to Hannah's job as product manager, covering them properly, getting it right, that's the hard part. And I would broadly say that companies that go on for too long about how proprietary their technology is and how much they have to defend their IP are, in many cases, an instance of what Nikita Khrushchev told his son back in the Soviet days. We might have nothing to hide, and we must hide the fact that we have nothing. What differentiates us is, in most cases, the data every bit as much as the software. And I'll ask, there actually was, I didn't expect we were going to show anything with proprietary information markings on it. But I was surprised by one item that day, and feds are great in this regard. I don't have to put anyone with the US government under NDA. They're automatically under NDA if something is properly marked as proprietary. So there was one document the whole day we showed that had a proprietary marking on it. Can anybody guess what document that was? Zach gave it. It was our annotation guidelines. There's not a whole lot that's secret. We can tell you the technology. Kafir got up here and told you some of the details of how we do some of this pixie dust level magic. But the one thing that actually came up that whole day that was proprietary were the annotation guidelines. That can be the hardest thing to get right. And to Peter's question earlier about what can the machine learn, nothing more than what the humans can teach it. We are dependent entirely for the quality of what we produce, and in many cases are differentiated by our annotated corpora. This is not just documents, although we have that as well. It's also things like names and how they match across languages and scripts and cultures, and for that matter, the various things that machine databases do to mangle human names. All of that goes back to annotation. When you're evaluating technology, we'll get to this in our panel later, you need some sort of gold data set against which to evaluate. You may provide some of that set for training, reserve some for testing, but it really comes down to a question of, is all that glitters gold? How good is gold? And with that, I'll introduce Zach Yocum. He is an NLP expert, a computational linguist, and what he does all day is work on annotation. He's going to go quite deep. Some of the depths he goes to may actually only be comprehensible by about 20% of this audience. But I've also asked him to keep bringing it up to the mission level. So if you lose track of him amidst all the Greek letters, just take a pause and he'll come back up to why this matters to you. Zach, please take it away.
Thanks, Chris. Thanks for the introduction. I want to echo a few things from some of the other previous talks, and I'm going to introduce a few new things. I'm a senior linguistic data engineer at Basis, and what I'm going to be talking about today is how you measure inter-annotator agreement. So this is when you're creating a data set from scratch, or you're evaluating a data set that you found from a data provider or out in the wild. So the first thing to do here is I want to motivate everything by talking about a blueprint for a machine learning application at a high level. This is more applicable to supervised machine learning, but it also ties into other kinds of machine learning. If you were to try to learn from data that was not manually annotated, you would still want to have an evaluation set, and you would want that to be manually annotated. So the basic flow here is that you're going to have some human annotators. You're going to provide them with guidelines about the task you want them to perform, and you provide the raw data as well. And then with those components, you perform the process of annotation, of marking that data up in a way that is meaningful. And you produce a gold standard data set, or you hopefully do. And the metaphor here is that a gold standard means high quality. And then you use that gold standard data, and along with machine learning, to produce a learned model. And you can evaluate how that model works, the accuracy of that model, also using some held out set of your gold standard data. So the reliability of that annotation process and the quality of that gold standard, whether it really is gold or not, that affects the quality of your output, which is your model, and that's going to be used to make predictions that can have real-world consequences. So you want to ensure that the input is high quality. And so, I don't want to extend this metaphor too far, but there is this notion of fool's gold, right? You don't want to assume something is gold. You want to actually measure it, or at least if you want to be scientific about it, which we do. So there are 3 metrics that I'm going to cover here. And so the first being F measure, which is typically used not for measuring inter-annotator agreement necessarily, but it can be used that way. And I'm going to talk about how you might interpret that. And then I'm going to cover a couple metrics that are actually intended specifically for the purpose of measuring the level of agreement between multiple annotators. So there's going to be some math, but don't worry about it. I'm not going to quiz you on it. F measure has been mentioned a few times, and I want to just unpack it a little bit and try and help us understand what the purpose of this measure is and how it's computed. So F measure is composed of 2 other metrics, precision and recall. And this metric comes out of the field of information retrieval, where say you have a search engine and people are putting a query into that search engine and they're getting results. You want to measure how accurate are those results. So some very intelligent guys came up with this metric, and what it allows you to do is it allows you to balance precision and recall in a certain way. And the reason you want to do that is if you put in a query to the search engine, you could have the system return every document in your index. And that would give you perfect recall because you wouldn't have missed anything ever. You wouldn't get any false negatives. Whatever the user might have wanted to get back, it's in there somewhere. Versus precision, where if you wanted to get high precision, you could imagine a system that just returns the top result, the one document that you're highly confident that is relevant to the query. And you could do each of these things, but those systems would not do well in terms of F, because the one that was very precise but lacked recall, that would get penalized for all the false negatives. And the system that was high in recall but not precise would be penalized in terms of false positives. So the point is that F combines these metrics in a way that you get a sense of overall accuracy that is balanced, and there's not really a feasible way to cheat on this kind of metric. If you're going to sacrifice precision for recall, you can do that, but you won't. F will reflect that, or vice versa. We can look at a couple examples here. So really, I've described F in terms of measuring the accuracy of a system making predictions against some gold standard. But if we want to use F to interpret the agreement among annotators, we don't have a gold standard yet. That's what we want our annotators to produce for us. So if we look at some example data here, we have a couple of tweets here that have been annotated with sentiment judgments by 2 annotators, A and B. And we're not going to talk about what is correct here. That is a job for the annotation guidelines to tell the annotators how they should do this in a way that results in judgments that we believe are correct. What we're trying to do here is we're going to try and measure the level of agreement between the annotators, whether they are consistent, essentially, or reliable in their making their annotations. So if we take the first tweet here, annotator A might annotate it with a smiley face, and annotator B might annotate it with a frowny face. And if we designate annotator A to be a stand-in gold standard, then we can use F measure to essentially say annotator B is making a prediction against what annotator A annotated, And then we can describe these annotations in terms of the error types in which F measure is defined. So we could say that if we designate annotator A as gold, then annotator B's frowny face is a false positive, and it's a false negative for what annotator A annotated, which was the smiley face. So the point here is that the precision and recall, against the sensitivity to false positives and false negatives, changes depending on which annotator among the pair you designate as your gold standard. So you have to be careful about how you're interpreting F measure when you use it for inter-annotator agreement. So you can get a sense of how much annotators disagree relative to the other, but you don't interpret this in terms of correctness. That's how it would be used when you're evaluating a system making predictions. In this case, this is really measuring reliability, not accuracy. And that's an important distinction to make. So F measure has nice properties for doing evaluation. It's a score that ranges from 0 to 1, and 1 would mean perfect accuracy. It's got the nice property that it's sensitive to both false negative errors and false positive errors. And it has some drawbacks for, not necessarily for doing evaluation. It's really good for that. It has some drawbacks if we try to interpret it for inter-annotator agreement. It measures accuracy with respect to a gold standard. And so we have to designate something to be the gold standard, even when we're not sure that it actually is gold yet. And the other con is you can't compare it across different data sets or different annotators, or even a different annotation task necessarily. So again, it's with respect to some gold standard that you're measuring, and if that gold standard is different in a different task, then whatever number that you compute is not necessarily interpretable in the same way as in a different situation. So the next metric I'm going to discuss solves some of these problems. So we can more directly measure reliability in a way that is more appropriate. So the Kappa score was introduced as a way of measuring agreement that you take independent annotations from parallel annotations on a data set, and what you do is you measure different components. You measure the level of observed agreement in the data set, and then you measure the expected agreement. And the expected agreement here is it's essentially measuring what level of agreement you'd expect if your annotators were annotating at random. And so this is a good way of capturing agreement above chance. And that's really what is interesting about this metric and what makes it a good metric. It lets you measure the reliability relative to chance agreement. And if you have an annotation task, there is a possibility that if your annotators were annotating at random, that they would agree some amount of the time. So that's where computing the expected agreement is important. And another property of Kappa, there's a generalized form of this metric that was introduced that allows you to measure agreement across a set of annotators more than just a pair. So with F measure, you essentially you can compute F pairwise across pairs of annotators, but you'd have to just take an overall average if you wanted to get a sense of a pool of more than 2 annotators. And Kappa actually directly is computing, the generalized form can compute over a set of annotators to achieve one metric, or you can still do the pairwise measure. So what Kappa is doing here is it's saying, what if we had unreliable annotators? We would want our metric to be able to interpret that and keep that as part of the way we measure the reliability. So if you were to have annotators who were annotating at random, then Kappa will account for that. And so Kappa is a little bit different than F. The range of scores you can get range between -1 and 1. And there's an important point on that scale, which is 0. And a Kappa score of 0 means that your annotators for that data set, they were not annotating any better than if they were picking at random. And so the pros here are we can measure the level of agreement above chance. So scores from between 0 and 1 indicate agreement above chance, and 1 being perfectly, your annotators are in perfect agreement. And we can annotate, we can have a set of annotators that's more than just a pair, and we can still compute one value to measure the entire set. So these are nice. The only issue is that Kappa assumes you have a particular kind of data, which is data annotated with nominal labels. So an example of that would be going back to Kafir's example of fruit. So we would consider, or one might consider, a model where your labels for fruit are nominal, that the labels are the same if the fruit is the same. You know, if you have two annotators who both say, yes, that's a peach, then the annotators are in agreement. But if the annotators pick two different fruits, it doesn't matter which they are, then they're equally in disagreement. Whereas saying maybe, I don't know, a peach and a cherry are more simpler than a peach and a cantaloupe or something like that. And so it's important to think about what kind of data you have. And so that brings me to the next metric, which is an alpha score. And this is similar to Kappa in that it takes into account observed agreement and expected agreement. But it introduces another tool that lets us sort of massage the metric to account for the specific kind of data that we're working with. And that's important. You don't want to consider all data the same because it isn't. So what alpha does is it has a parameter which lets you input a function that measures the distance between any two data points in your data set. And basically, this is just the point that if we have if we have a nominal set of data, then if we have a point A and a point B in our data set, then the difference between these is 0 if they are the same, they're identical, and it's 1 if they're not. And those are the only ways that we would measure a difference. What alpha lets you do is you can input any other kind of delta that you want. So one useful one might be an ordinal delta. And what this accounts for is if your data points fall on some kind of a scale, like say, the polarity scale for sentiment. So we can look at the difference here, and it's a little bit subtle, but it's important. If we look at the delta nominal and delta ordinal between three sentiment values, say a smiley face, a neutral face, and a frowny face, they're the same if the annotations are the same. But if we look at the difference between annotator A marking a frowny face and annotator B marking a smiley face, the nominal difference there is the same as 1, as if annotator A annotated a frowny face and B annotated a neutral face. But if we look at the ordinal difference, there's a greater difference between the frowny face and the smiley face. And so we want to try to account for that. Whatever kind of data we're looking at, it's important to try to understand the connections between those data points. And if they do fall on some kind of a scale that's not nominal, we want to come up with a delta metric that matches to the situation. So you can come up with any number of different kinds of deltas. Alpha doesn't care. It just has to be of the form that I described earlier. And depending on the kind of data you're dealing with, there's lots of kinds of deltas that are already well defined, and you can just take those off the shelf. Sometimes you come up with a data set that you need to come up with a custom metric because it's something that no one's been working with before or you haven't seen described. But you can just define that metric as you see fit. So let's take an example. So this is a few data points taken from a corpus called the Stanford Sentiment Tree Bank. And what this corpus, how this corpus was annotated is it was a set of movie reviews, and the annotations were performed for every word in the corpus. There was a sentiment judgment applied on an ordinal scale from 1 to 25. And then they also went another step further, and they annotated. They parsed these with a syntactic parser, and then they had the annotators annotate all of the nodes in that parse tree with sentiment values. So you can see sort of the sentiment percolates up this tree, where the root node in this visualization shows the sentiment for the whole sentence, and then as you go deeper down, you get to the level of. So for instance, the sentiment value assigned to U was 13 because that's a neutral sentiment on the scale from 1 to 25. And so for instance, you see that love got a higher score on that sentiment polarity scale, closer to 25. And so what they did is they had 5 annotators annotate all of the nodes in all of the trees in this corpus. And you can take those annotations, they provide that along with the rest of the data, and you can compute an alpha score. And so when you compute the nominal alpha score, which again treats data points as similar, it's the same if they're identical and different if they're not identical, and you get an alpha score of 0.19. And if we think about that scale from -1 to 1, where 0 is chance agreement, this is closer to chance agreement than it is to 1, perfect agreement. So that's not a very good alpha score. If we choose the appropriate delta metric, in this case an ordinal delta, where we consider that ordinal scale from 1 to 25, where 2 is greater than 1 and 3 is greater than 2, and so on, we get an alpha score of 0.57, which is closer to 1 than it is to 0. And so this is sort of an extreme case, but it illustrates why you would want to choose the appropriate delta metric. And so this is illustrative of why we would use an alpha score, and this is a good demonstration of how we would compute it. So to review here, so alpha is also on a range from -1 to 1, just like kappa, and a 0 alpha score indicates agreement no better than chance. And alpha is really ideal in this case for measuring reliability, because we're measuring agreement relative to chance. We can measure agreement between 2 or more annotators. We can account for any kind of annotated data that we might encounter. And it's actually even also got some nice benefits, which Kappa doesn't, including the ability to tolerate missing data points. So you could imagine in the real world, if you have your annotators working away, and one of your annotators quits because they have to go do something else. If some of your data points were annotated by 5 annotators, and some of your data points were annotated by only 4 annotators or 2 annotators, alpha can account for that, and you can still compute a metric. So how do we interpret these scores? So I showed a couple scores on the Stanford Sentiment Tree Bank. If we look at the literature, there are recommendations about how we might interpret these scores. So some recommendations will tell you, well, you need a score of 0.8 or better, or your data is not reliable enough to draw conclusions from. And there's also suggestions about reporting more than one metric. And that's also a good idea. If you have the data, you can compute any number of metrics that you want, and you can compare them. So another recommendation from the guy who actually invented alpha scores, he recommends an alpha score of greater than like 0.667. That's probably reliable enough, but you'd probably prefer agreement above 0.8. So really, the thing to keep in mind here is we want to achieve reliable annotations, because that's going to affect the quality of the models that we're producing at the end of the day. If we can't achieve reliable, if we go through the annotation process and we make a measurement, and that measurement is not acceptable, what does that indicate? So this can be explained in many different ways, but some of the things that it might indicate are that maybe your task isn't well defined. Maybe the kinds of the labels that you've chosen don't adequately represent the kind of data that you're looking at. And it may be worth asking your annotators, hey, are we missing some labels here? Or is this a good way to try to model the data in the first place? It could mean that the annotation guidelines that instruct your annotators about how to go about the task are not sufficient. Maybe they're confusing. Maybe they have examples that are not the way that you would prefer your annotators to annotate. Or maybe it means you have some annotators who are not performing the task the way that you intended. And one way to figure that out is you can compute these annotation metrics in a pairwise way, and you can look at the annotation across each pair of annotators. And in that way, you can identify annotators who are not performing well relative to the rest of your pool of annotators. So that's an important thing to do in the case when you see an overall score that's not so great. You can go then look in pairwise, and you can identify, and you could kick out an annotator. You could say, hey, thanks for your time, but you're not annotating in the way that we expect. So to recap here, there are advantages and disadvantages to these metrics. F is serviceable. Kappa is also serviceable, assuming you have nominal data. And alpha is really ideal for the purposes of what we're looking to do here. There's a caveat here, which is that you can define F in different ways. You can define your error types in different ways to account for different kinds of data. And that's also definitely a good idea. If you're doing, say, the task of named entity recognition, there's some ways of computing F measure that are recommended by the Machine Understanding Conference, these MUC MUC scores. And so you can look to different ways to evaluate your data. But for doing inter-annotator agreement measurements, alpha is really a really good metric. It does everything that we want it to do. So I thought I'd just leave with some takeaways here. When you're creating your own annotated data set, always measure inter-annotator agreement. If you're assessing a data set that's public, confirm the published IAA if you can find someone who has published inter-annotator agreement scores along with their data. Even if they haven't, you can still take some sample of their data and annotate it yourself and see that your annotations are reliable with the data that was published. And be wary of data sets if the authors don't publish reliability scores. You don't want to rely on unreliable data because you'll start using that data for downstream applications and you'll find that things are not working as well as you think they should. And one of the reasons might have been that the data was not reliable in the first place. And a broader takeaway is interpret measurements. Don't crunch numbers without thinking about what those numbers represent and how they are computed. I think a lot of the time, sometimes in this field, we're guilty of thinking about, oh, well, we got 0.01 higher F score or something like that. And is that actually really indicating that you did a better job? There's some arguments to be made that that's not an important distinction to worry about. Really, what you care about is the quality at the end of the day. And there are lots of different ways to measure that, and we should consider all of those ways. Just cite some of the sources in the literature here, and the Noun project, which is a nice Creative Commons set of icons. So thank you. Any questions?
So I have a few comments or questions because this is the problem we ran into in our project. So when you, in the ideal world, you will say, well, if a human is asked to annotate whether this picture has a cat or it doesn't have a cat, it's a pretty simple case, so you would expect them to, annotators to be in agreement. But there's an argument to be made that in any realistic annotation task, the problems are so subjective that a show of a high inter-annotator agreement might be a sign of things that are, maybe this task is oversimplified for them. And so, a question to you is, do you know if, it's very easy to say, well, the kappa is 0.4, so our annotation is unacceptable. In realistic sense is that, well, what else have you got if you drop those annotations? So one question is there a way, do you know of rigorous ways of estimating how accurate, so suppose you have a data set, right? You annotated it, and then you used it to evaluate your classification algorithm, right? So you got an F score of whatever, 0.8. Is there a way to say how reliable, rigorously, how reliable that F score is as a function of the inter-annotator agreement? Because in reality, that's the best you can do. You got yourself an expensive annotated corpus. Your inter-annotator agreement is low. Are you going to what? Just throw it away? So the idea would be, so it would be really great if there were any sort of quantitative measures that would say, your classification algorithm got an F-score of 0.6, but the reliability of that metric is this based on the annotated agreement numbers.
So I think, so the answer to the question overall of whether we can rigorously use Inter-Annotator agreement metric to tell us the quality of the accuracy is no. It's measuring something different. And that goes back to why we have to be careful about how we interpret F-score if we use it to compute Inter-Annotator agreement, because it is not measuring how correct your one annotator is relative to the other. Well, it is doing that assuming that one annotator is correct. It does not tell you, they're not equivalent. And so what I would say is that you can use these scores, the Inter-Annotator agreement scores, as an estimator of what you would expect for your F-scores for a good system. In the sense that if you were to use two different data sets, one that was more reliable than the other, you would expect a better F-score from the system that learned from the more reliable data. But that, I would say, it's an estimator. It's not a rigorous way of doing that. The other thing that I would say is that depending on the annotation task, so if you're doing a task where you expect it to be subjective, then you can tolerate less reliable data. So that's a case for sentiment analysis. So it is actually incredibly difficult to get Inter-Annotator agreement metrics to get above, say, 0.66 on sentiment analysis. It's just a subjective task. And you might even argue that the task is just not very well defined, that, say, compressing all the information in a document down to the 3 label or 2 labels or whatever number of sentiment judgments that you allow in your model, that's not even a particularly interesting or well-defined way of judging sentiment. So you might want to go deeper to some of the instances like that Chris showed earlier, where you're looking at an entity level sentiment. Well, what's the sentiment of this particular entity in a document? That might be something that is a little bit more, it's maybe less subjective at least, but it's still probably difficult to achieve high reliability on. So I hope that helps a little bit. I don't think I do have an answer to the overall question.
Annotation is expensive. Can you comment on how you might want to measure and exploit what is essentially a dirty, implicit kind of data? That is, say that same search, an image search for Siamese cat, you won't get people explicitly telling you whether there's a cat, but you could get massive amounts of data where they do or don't click on, buy, click past the first set of images, and so on. So you have much cheaper dirty data. How would you use that?
You can use it. You have to measure how well it helps. So I think that's sort of so I raised at the beginning the point that I'm really talking about supervised learning, where you're asking your annotators to do the direct task that you expect the machine to perform at the end of the day. What you're describing sounds more like semi-supervised learning, where you have an indirect signal, but you still hope to learn from it. And it can work. There are instances where that would be possible. I'm not prepared to speak to anything in particular at the moment, but I do know that that is a possibility. And you would still want to measure the reliability. So in this case, your annotation signal is really the clicks. And so you could compute the reliability of clicks versus non-clicks as a binary judgment, and then considering that as an annotation. So, yeah.
Ready, over here. So I was going to say to the one gentleman's question here, there are other measures to use other than F measure and Kappa and alpha. There's Pearson's correlation, which is used a lot in NLP. So what I guess I would suggest is look at multiple, because I mean, these aren't the be-all and end-all decision points, because it's a good point you make. You don't want to be sort of binary about making these decisions. So
yeah, that's a good point. I have not covered the whole space of metrics here. There are definitely others, and that's the recommendation really in the literature, is provide multiple metrics and interpret them. So that's definitely a good point. And I would say correlation coefficients like Pearson those are nice, but the quality that they lack that Kappa and Alpha have is that those metrics don't measure agreement relative to chance agreement. And I would say that when you're doing any kind of task where there is a level of chance agreement, then these metrics would be slightly more appropriate.
How do you think about weighting disagreements between annotators depending on how difficult the particular sample or the task is? Is there a way to do that?
Please restate the question.
Yeah, so the question is, how would, say you had a group of annotators and you have some belief in the quality of that some annotators are giving you better annotations than others, and how would you weight that? That's a little bit, goes a little bit outside the ability of these metrics to tell you what to do in that situation. One of the things that you need to do when you're creating an annotated corpus is to go the last mile and get that standard that you're going to say that this is what we're going to use as the reference corpus to learn from and to evaluate against. You need to do something called adjudication. So if your annotators do disagree on a data point, you need to come up with a singular label that you're going to say this is correct at the end of the day. And to do that, what you would typically do, I mean, so in the Stanford tree bank, they actually took 5 annotators' data points, and they said, well, if they disagreed, we'll just take the average of all the data points, and we'll say that's the gold standard. I actually would recommend against that. It may be time-consuming, but you will get a higher quality data set at the end of the day if you adjudicate those disagreements by having one of the annotators you trust more to go look back at those disagreeing examples and give a final answer. And sometimes that final answer might be different than both of the original annotations that you got in the first place. So that would be my recommendation there. I would say that weighting annotators together is probably not important as the adjudication process to arrive at a better quality data set. All right, thanks.
Zach, thank you.